Again, this is chapter 30. Problem number 33. So problem 33, we're asked, what energy photons can pump chromium atoms in a ruby laser from the ground state to its second and third excited states? And then it asks us, what are the wavelengths of these photons? And verify that they are the visible part of the spectrum. So to do this problem is really, really hard unless you kind of look at the previous problem. The previous problem is 32, where they have a ruby laser. And they give you the energy states for a ruby laser. Okay? So the energy states for a ruby laser, we have the ground state that has 0 electron volts. We have the first excited state that is at 1.79 electron volts. And the picture I'm drawing here is called an energy level diagram. It kind of traces out all the different energies of the electrons inside of this chromium atom in this ruby laser. Second excited state is 2.3 electron volts, and the third state is 3 electron volts. And for part A, all they want to know is what energy photons can pump in a chromium atom from the ground state to its second excited state. So what energy do I need to have come in here to convince the electrons to absorb so that they jump up to the second state? How do I find that energy? 2.3 electron volts. So to go from ground to the second state, I need 2.3 electron volts. How about to go from the ground to the third state? What energy do I need? 3 electron volts. Let's go off book. If I wanted to go from the first state to the third state, how would I figure that out? 3 minus 1.79. What is that? 1.21 electron volts. Okay, so that's part A. The way that you do that is look at problem 32 and then go from there. Okay. So now the next part is what are the wavelengths of these photons and verify that they're in the visible part of the spectrum. So this one I think was where the main question was. And it requires remembering some physics that we've learned previously, knowing that energy is defined as h times c divided by the wavelength. It's the definition of energy in terms of wavelength. E equals hc over lambda. Take the whole bowl. Yeah. I have no idea if any of this stuff works. Okay, so if I want to find wavelength, how can I find wavelength from this? What do I need to do? Do some algebra. Yeah, so I can move lambda over to the other side and move e down to the bottom. So multiply both sides by lambda and then divide by e. And I can get the equation lambda equals h times c divided by e. And I think probably the part that tripped people up here is what to actually plug in for all these things. Right? We have a value for h. H is Planck's constant. Usually in the past we've used Planck's constant in terms of joules times seconds. You can do that, you can plug it in joules times seconds, but what are our energies in? We have all these energies. What are the units of these energies? Electron volts. So if you write Planck's constant in terms of electron volts, then you can get your answer all in one swoop. Yeah. So Planck's constant in electron volts is 4.136 times 10 to the negative 15 electron volts times seconds. So if I plug that number in, I can get the wavelength from ground to the second excited state by plugging in h is 4.136 times 10 to the negative 15. C is the speed of light. What's the speed of light? 3 times 10 to the 8th. And I divide by the energy difference that I'm interested in finding the wavelength of. That energy difference from ground to second state, from 0 up to 2.3 EVs was 2.3 electron volts. So I plug in 2.3 EVs. When you plug all those numbers in, you should get about 5.39 times 10 to the negative 7 meters, which is 539 nanometers. That's in the visible range. That's around green. So I'm going to suggest everybody, once you're done writing, go ahead and take out a calculator and make sure that you can plug those numbers in and get those answers. Make sure that you can get that. So we do the same exact procedure to get the wavelength of 414. Just plug in your new energy. The questions on that one? Is that more straightforward now? Good. So let's do now the fun stuff. I kind of like this part of atomic physics. It's just a puzzle. That's all these are. It's just knowing what the puzzle is actually asking you to find. So quantum numbers and rules. Normally with quantum numbers, there's a whole bunch of things that are listed in these kinds of sections, but the quantum numbers, there's only really 4 of them. What are the 4 quantum numbers? Do you remember? N, L, M sub L, and M sub S. N is called the principal quantum number. Starts at 1, 2, 3, so on and so forth. It's just an integer. And then L, what is L called? Is it the angular momentum? Yeah? And this is the angular momentum quantum number. You can use this to actually calculate the angular momentum. And if you're calculating the actual angular momentum, then you're calculating big L, which depends on this quantum number. If they ask you specifically what is the angular momentum, they want big L. If they ask you the quantum number, they want little f. That's mostly what I'm going to be asking you to do, okay? Getting that little angular momentum quantum number. And what is that value? Where does it start? There's some rules. Where does angular quantum momentum number start? Starts at 0. And what does it go up to? All the way up to n minus 1. So the angular momentum quantum number is determined by whatever your principal quantum number is. If my principal quantum number is 1, then I start at 0, I go all the way up to n minus 1, n minus 1, 1 minus 1 is 0, so 0 is the only angular momentum quantum number I have. If I have principal quantum number of 2, then I can have 0 and I can have 1. If my principal quantum number is 3, I can have 0, 1, 2. Okay. Keep those rules in mind, and we're gonna apply them in a problem in a moment. So, what's the M sub L? Orbital angular momentum. Somebody took good notes, or has the right page in the book marked. This has some rules too. What can the values of this be? They depend on L. I can go from negative L all the way up to L. And then M sub S. That was the spin, and the spin is the easiest one. What's the spin? Positive or negative 1/2. Has to be one of those two. So I think most of the questions I ask you about quantum numbers, they are involving these 4 different things. All lowercase letters. Lowercase is different than the uppercase. So number 37, they ask us what are the possible values of M sub L for an electron in the n equals 4 state. So we basically have to figure out what are all the n equals, all the M sub L's if n is equal to 4. So you have to keep these rules in mind. Let's shrink those down. Kind of keep them up here in the corner. So this is 37. It asks us, what are the m sub l's if n is equal to 4? So we have to go step by step. If n is equal to 4, that determines what all of our l's can be. What l's can I have if n is equal to 4? Well, I start at 0, and I go up to n minus 1. So I could have l equal to 1, I could have l equal to 2, I could have l equal to 3, and the way I like to do it, I just start, whatever my n is, I list all the numbers between 0 and that n, all the way up to 4. Can my l be 4, though? No. Okay, so I have to go all the way up to the n minus 1. So I can have 0, 1, 2, or 3. And then underneath this, I can write all the m sub l's. And the m sub l's depend on my l's. So each one of these little columns is going to have multiple m sub l's that you could have. M sub l goes from negative l all the way up to l in increments of 1. So if I have l equals 0, well, I go from negative 0 to 0. That's just 0. If I have l equal to 1, what can my m sub l be? Negative 1, 0, 1. If my l is 2, what can I have? Negative 2, negative 1, 0, 1, 2. If I have negative 3, or if l equals 3, negative 3, negative 2, negative 1, 0, 1, 2, 3. Remember this from chemistry? You should have done this in chemistry. So we're just listing quantum numbers. So those are all the m sub l's that I can possibly have. Okay? Any questions on number 37? Yes, please.
Since there's repeats, like, can you just say negative 3, negative 2, like the last column, because there's repeats between?
Sure. If they so this question asks what are the possible m sub l's, you could list just these ones.
Okay.
If I ask you for every single quantum state, then you would need to list all of these.
Okay.
Because each of these pairs are unique. So 2 with negative 2 is unique from 3 with negative 2.
Okay.
Yep. So let's do another one, unless there's questions. Any other questions? No?
So what was the answer for that specific question?
This would be fine for the answer. But all of this could be the answer. But if you're really good with the rules, you can jump straight to this. These are the m sub l's. Negative 3, negative 2, negative 1, 0, 1, 2, 3. The shortcut would be, okay, n equals 4. That means l could be 0, 1, 2, or 3. 3 is going to have the most m sub l's, so list all the m sub l's for 3, and there you go. Yeah. I don't like to think that much, so I just brute force and write everything down. When I think a lot, there's burning, and that's not good. My brain burning. Okay. Let's do number 47. Makes me sound like a pyromaniac. So number 47, this is more the type of question that you would see on something like an exam. List all possible sets of quantum numbers for the n equals 3 shell and determine the number of electrons that can be in the shell and each of its subshells. And then show that the number of electrons in the shell equals 2n squared and that the number in each subshell is 2 times 2l plus 1. So to answer this, we should know what's a shell versus what's a subshell. So which quantum number represents a shell? N represents the shell. And what quantum number represents the subshell? L represents your subshell. And I know the number of electrons in each of these. How many electrons are in the shell? 2n squared. And how many electrons are in the subshell? 2 times 2l plus 1. And how do we know that? How do we know those two equations are true? It's in front of us. They tell you it in the problem. Okay, so they kind of give you right away what you're looking for. And what did they want? They wanted us to list it for which one? N equals 3 shell. Okay. N equals 3. So right away, I should be able to tell you how many electrons are going to be in this whole shell. So I know how many states I'm going to have to write. Because I can write the number of electrons is 2 times 3 squared. What's 2 times 3 squared? 3 times 3 is 9, times 2 is 18. So that tells me how many electrons, how many different quantum states I need to write. I'm going to have 18 different ones. Yep. N equals 3, 2, 3 squared equals 18, equal to 2n squared electrons. That tells me how many pairs of quantum numbers I'm going to have. So now I can actually start writing out the table of the quantum numbers that exist for this one. Okay? All right. This gets nuts. So I like to make a little table of n, l, m sub l, and m sub s. What is my n? My n is 3. They've told us that. I know n is 3. What l's can I have? I can have 0. If L is 0, what is M sub L?
0.
M sub L has to be 0. And what's M sub S? Plus or minus 1/2. There's 2 electrons. I could have an electron in the state 3, 0, 0, positive 1/2, or I can have 3, 0, 0, negative 1/2. 2 states right there. So now I need, how many more do I need?
16.
I need 16 more. Okay. N can be 3. What else can L be? L can be 1. If L is 1, what can M sub L be?
1.
Negative 1, 0, or positive 1. And then what can M sub S be?
Plus or minus 1.
Plus or minus 1/2. How about right here? What can M sub L be?
Plus or minus 1.
Plus or minus 1/2. I did some crazy writing there. I went negative 0. Negative 1, 0, 1. Positive or minus 1/2. My L is still 1 here, and my N is still 3. How many electrons do I have now? 2, 4, 6, 8. I'm up to 8. How many more do I need? 10 more.
This is not my
Okay, my N can be 3. What else can L be? 2. Okay. If L is 2, what can M sub L be? Negative 2, negative 1, 0, 1, 2. Positive minus 1/2, positive minus 1/2, positive minus 1/2, positive minus 1/2, positive minus 1/2. 2, 2, 2, 2, 3, 3, 3, 3. How many more electrons was that? 2, 4, 6, 8, 10. How many do I have to? 2, 4, 6, 8, 10, 12, 14, 16, 18. There's my 18 electrons. That's all of them. Now, how many are in each subshell? How many subshells do I have here?
No. 9.
Nope.
3.
Subshell is determined, bless you twice. Subshell is determined by your L.
3.
So I have 3 different subshells. I have 0, I have 1, I have 2. Each one of those is a subshell. So there's one subshell, there's another subshell, and there's another subshell. How many electrons are in each of these subshells? How many electrons are there in the L equals 0 subshell? How many should there be? There's an equation to figure it out.
Oh.
The electrons in the subshell is 2 times 2L plus 1. So if I have 0, 2 times 0 plus 1. What do I get there? I have 2 multiplied by 2 times 0 plus 1. What's 2 times 0? 0 plus 1?
1.
1 times 2? 2. I get two electrons.
No,
That's a colon.
That's yeah.
Okay. If L is equal to 1.
Quantum numbers can't have those.
Yeah, please.
Kind of lost.
Oh, you lost? Okay. So I want to know, how many electrons can I expect in a subshell? Subshell is determined by your L, whatever your L number is. Yep. L is 0. This is the equation that lets us figure out how many electrons are in that subshell. So I plugged in 0 for L.
So for that, you would only do it once for each subshell. So 1 for 0, 1 for 1, 1 for 2?
Yep.
Okay.
Yep. So I should have 2 electrons in the L equals 0 subshell. Here's my L equals 0 subshell. I have positive or negative 1/2, so I only have 2 electrons there. Okay. Let's see what it looks like for the L equals 1. If I plug in 1, 2 times 2 times 1 plus 1. What number do I get? What's 2 times 1? 2 plus 1. 3 times 2, 6. I should have 6 electrons in the L equals 1 subshell. The L equals 1 subshell is made up of this guy, this guy, and this guy. So that's 2 electrons plus another 2 plus another 2. 2, 4, 6. 6 electrons in that subshell. L equals 3. 2 times 2 times 3 plus 1. 3 times 2 is 6, plus 1 is 7, times 2. I plugged in the wrong L. Right? We don't want 3, we want 2. Two times 2 is 4, plus 1 is 5, times 2 is 10. So I want 10 electrons. Do I have 10 electrons? How many here? 2, 4, 6, 8, 10. 10. So I got all my subshells, and then if I add up all the electrons, 10 plus 6 plus 2, I get 18. So it all works out consistently. Okay. This would be the full quantum number state if n equals 4. What could I ask on an exam? I could ask for n equals 3. That'd be fewer states. That'd be easier. I could ask n equals 5. How many states would I have for n equals 5? Yep. 2n squared, 50. So you write down 50 states. Start with Alaska, Arkansas, Alabama. I don't think I can name all 50 states. I've seen it on Animaniacs. Any questions on this one?